All right, so let's get started. Let me start with some announcements. I presume if you have been checking posts on Piazza, you know that we put out a lab already. Lab 1 is out. It's due at the end. I think it's due either the end of the month or in early part of the next month. Okay, so you have 2.5 weeks or approximately 2 weeks and couple days to complete it. So please get started. Don't wait till the last minute. You always will find that you needed a little more time than you thought you needed to complete it. So the earlier you start, the better off you will be in terms of getting it done on time. Okay, the lab talks about using remote procedure calls and RMIs. We already spoke about all of those topics. So the class will actually make you write some code to write some simple applications that use these concepts. Okay, so that's really the goal of the lab. The other thing that you will use in the lab is concurrency, which the basic concurrency concepts you should already know from using threads, hopefully, or learning about threads, but I'm going to cover it again today. So that will be the other aspect that you need to know for the lab. Okay, so that brings me to today's topic, which is concurrency in distributed systems. So I'll basically first reintroduce threads for those of you who already know what threads are, and if you don't, this is basically the brief recap of what you should know basically about threads and synchronization. So we will do that first. Then we'll talk about concurrency models that you can use using threads or similar functionality to build server applications. That's really what you will use for the lab. And then at the end, I'll talk about how threads are scheduled. And that will basically lead us to further topics on scheduling for next class. All right. Okay. So let's get started here. We will start with this notion of threads and concurrency. So this is really a recap of what is a process, what is a thread within a process, what are differences between threads and processes. Okay, so what's a traditional process? Okay, essentially the undergrad OS definition of a process is that it's a program in execution. Okay, so you have a program that you write. When you run it, essentially the OS creates a process to execute that program. Okay? But what does that actually mean underneath? So if you think about any process, okay, it has some memory allocated to that process. Okay, so the program is actually loaded in the memory of this of the machine. Okay, and then that is called the address space of that process. Okay, so memory region, the memory allocated to a process is referred to as its address space. The address space usually has code and data that belong to the process. Okay? The code is the code that the process is going to execute. The data is essentially variables and other things that the process needs, and that is usually stored either in the stack or the heap. Okay, I'll show you some pictures in just a moment. But given this address space, okay, that belongs to a process, there's also something that's actually going to execute the code that is part of that process. Okay? So that is something we'll call a thread of control. Okay? So that's basically the part of the process that's executing instructions one at a time, right, in that process. Okay? So a traditional process has a single thread of control, which means there's only one instruction executing at any given time, and then you execute the next instruction, and there may be functions, so you might jump around in the process, execute some other part of the process, some other function, and come back, and so on and so forth. Okay? So it's a single thread of control. Okay? Address space is basically part of that process. Typically, address spaces are not shared unless you have something like shared memory, in which case part of the memory of that process is shared. But typically, the memory that's allocated to process is private to that process. The address space is not accessible outside the process. And then a process might have other resources like files that are open that it's accessing, or we already learned about network sockets that they are used for communication and so on. So those are also part of the process. Okay? Now, what's a thread and how is it different from a process? So you should think of threads as generalizing this concept of a process. Okay? In a traditional process, you have a single thread of control. There's only one instruction that you're executing at any given time. Okay? So you should think of a thread as a flow of control through an address space. And an address space might have multiple threads or multiple flows of control that are concurrently executing different parts of the process. Right? So the way you want to think about a process with multiple threads, which is called a multi-threaded process, is that this address space has multiple things that can execute concurrently. Okay? In a traditional process, only one instruction that can execute. In a multi-threaded process, multiple instructions can execute concurrently. Each instruction is associated with a thread of control. Okay? So all of these threads are going to share the same address space. So they have access to all of the data that belongs to that process. Okay? So it has access to the entire address space. And you can essentially get parallelism in certain cases if you have threads. Okay? Threads give you concurrency, and we'll see why they can also give you parallelism. So you can actually have parallel execution of code within that process when you have threads. Okay? And last but not least, whenever you have threaded execution, you need to use synchronization, because whenever these threads access shared data, you have to protect that with synchronization primitives like a lock. Okay? Otherwise, the data might be corrupted. If you have multiple threads trying to access the data at the same time, they might overwrite each other. So anytime you have multi-threaded processes, you need to have synchronization. Okay? This is essentially a high level the definition, but now let's look at some pictures to understand what is a thread and so on. So here is an example of a process. This rectangular box is the memory allocated to the process. Okay? It has different regions, which we'll ignore for a moment, but you can think of that as what's called a code segment. That could be the heap, that could be the stack, or something like that. Okay? But let's just focus on this as the address space. What you will see here is that you have these three boxes, which is called program counter register, and so on. Each of those smaller boxes is a thread, and that thread is essentially, this thread is executing this instruction in the process. Okay, that's the program counter that's pointing to that instruction. This other thread is executing this other part of that code segment, which is that instruction here that is pointed to by that arrow. And the third one is executing some other instruction. So now you have essentially multiple instructions within that process getting executed concurrently. Each is executed by a separate thread. Okay? In a single threaded process, you have only one of these. So you wouldn't have this. So there's only one thing executing in that process at any given time. When you generalize this to a notion of a multi-threaded process, there are multiple threads of control. There are three shown here. That number could be arbitrary, greater than one. Okay? So that's an example you should keep in mind. Each thread has its own program counter and its own register values. Okay? And it has its own stack as well. So this process, this thread will have this stack, this process will have this stack, but they share the heap. They share the code segment. Where the stack is unique to a thread, registers are unique to a thread. Okay? This is something you want to keep in mind. Yes. Question is, when a program runs, does the code get loaded into the address space? That's your question, right? So essentially, when a process starts execution, the code that is part of that program, okay, that you started executing is loaded and is called the code segment. Okay? Now, technically, the OS is not going to load the whole program, okay, because it uses a technique called paging. It will bring parts of the program into memory as needed. Otherwise, you will take a long time to start the process. But logically, you should assume the entire code is part of the process. Okay? Physically, it may not all be loaded in RAM all at once. It might be brought on into RAM on demand. Okay? That's clear? Or, yeah. Question is, what is the program counter? Is that your question? Okay. So I think this requires you to understand the basics of what a process is. Okay. This is exactly the kind of concept you should go back and look at an undergrad OS concept and do a book and understand what is a process, because it is inherent to understanding a threaded, multi-threaded process. But let me explain in any case. So the way any hardware works is there's memory and there are registers. Okay? So there are many kinds of registers. An important register is called the program counter. Okay? The program counter register points to an instruction that the program is going to execute next. Okay? Think of a program when it's loaded, it's not going to be Python code, right? It's going to be assembly code, because you will translate that code into machine code. So what is actually loaded is actually low-level assembly code. Those are set of assembly instructions. The program counter is the register that actually points to what's the next instruction to execute. Okay? So then we'll execute that instruction and sequentially go to the next one, unless there's a loop, in which case it will jump it. Okay? So So that's what a program counter means. The other registers store data values. Okay? There's also a register called a stack pointer that points to the stack and so on. You don't need to know every single detail here, but it's good to have a high-level idea of what a process is. Is this clear? Okay. So let's move on. So question is, why would you use threads? What kinds of advantages do they give us? As I said, a process can have multiple threads of control. Okay? When that process runs on a machine that has multiple cores or multiple processors, okay, each of those threads can now start executing on a different core. Okay? Then you get what's called parallelism. Okay? You are actually executing instructions in parallel. There are two or more instructions of that program that are actually executing in parallel on different cores. Okay? So this is going to give you parallel execution of the code of a process. Okay? So when you have threads, you can get parallelism. Okay? Now you will also get threads can also give you advantages even if you have a single core, which is concurrency, and I'll come to that in a bit. Okay? But if the main advantage is you can get parallel execution, so you can take advantages of the multiple cores you have on your machine and so on. Okay, switching, the other thing is switching between threads of a process is much faster than switching across between processes. Okay? When you have multiple processes running on a machine, the CPU scheduler will actually keep switching between processes, so it's time shared. Okay? The machine is time shared, so each process gets a slot to run. Okay? Now when you switch between two processes, that's called context switching or context switches. That's an expensive operation where you have to save the state of the process, load the state of the next process, and so on. Okay? But when you're switching between threads of the same process, that's much cheaper because the threads share the memory address space, so you don't have to save the memory state and restore the memory state. It's the same thing. Okay? So you only have to save the registers and load the registers of the next thread. Okay? So context switching between processes incurs higher overheads. Context switching between threads of the same process, much cheaper. Okay? So this reduces the context switch overhead on the machine. Okay? So you can actually make this more efficient. Also, thread creation, thread deletion, as you will see in later on in today's lecture, much cheaper than creating process and so on, because when you create a process, you have to allocate memory and so on. Okay? When you create a thread, the process already exists, so you don't have to reallocate memory. So it's much cheaper to perform some of these operations. Okay? Those are all advantages of having threads. I already said threads share the address space of the process and they execute in parallel. All right. So let's look at some examples. So this is a little more clear as to what threads do when they actually execute. Okay? So I'll start with a single threaded program. There's any program you write which has no threads, well, it will always have one thread, which is the main thing that's executing, but no additional thread. Okay? So here's a program. Okay? So you'll see that there's one function in the program which is called task. The task will just print something and go to sleep for 1 second, okay? And then print done. Okay? And here's the main program. Okay? It's going to execute sequentially. It'll cost task twice. This function is called twice. Okay? There's no threads here. So this execution is essentially going to sequentially execute that task twice. Okay? That's what is shown here. So this is the timeline of that execution. You execute the main program, it calls task, the task executes, and since it's sleeping for a second, the entire program will wait for a second until the sleep is done, and it will continue execution. It will come to the next function invocation, invoke the second invocation of the function, sleep for a second, then you're done. Okay? Pure sequential execution, very simple. Okay? Now the question we'll ask is, what happens when you use threads for this? It's very simple. Okay, program. Okay. Here's that same program with two threads. Okay. Now, rather than calling that task function is still the same. Okay. Rather than calling that sequentially, okay, as you did previously, we will essentially create two threads and ask each thread to execute one of that task invocations, okay, which is shown here. So you will see that you start and then you create the first thread, you create the second thread. Okay. You start the first and each thread is asked to execute the task. You start the first thread, you start the second thread. So these are now executing concurrently, not sequentially anymore. Okay? And so then you wait for them to finish. Okay? So now your execution looks like this. Okay? The single core at the moment, because we only have one processor and one core. If you have multiple cores, you will see a different picture, but assume it's only one core. Okay? So first the task starts, okay? Because that's one thread is starting to execute this task. Okay? While that task is running, since there's only one core, the second thread cannot yet execute. because there's only one core to run on, only one thread can run at a time. So this task essentially starts executing, and when it does sleep, okay, that task function is going to block. So it's going to sleep. Okay? CPU becomes idle, the scheduler will start executing the second thread. So you will see that there is no gap. You don't wait for a second to start executing the other thread. You switch to the other task. That is, you switch to the other thread here, started executing the other task, and then you sleep for some time, and then both of the threads are done. Okay, this is now concurrent execution, where you did not wait for the first function to finish. You started executing the second function while the first function was still executing and basically sleeping in this case. Is that clear? So you are now getting interleaved execution of multiple functions concurrently. All right. So that's very simple example of threads. We'll come back to more complicated examples in just a few minutes. Okay, but let's go back to what are some of these advantages. So we talked about single-threaded process. Okay, single-threaded process use blocking calls, have no concurrency. Okay, blocking calls means whenever you do I/O, okay, that entire process is going to block. It cannot continue execution until that I/O is finished. Okay, or if you have a lock or any operation that causes it to wait, means the whole process stops execution. Okay, so if you just had a single-threaded process, anytime you have any blocking operation, you do I/O, you write a print statement, okay, you try to read from a file, you try to grab a lock and you're blocked, the whole process has to wait until the operation is finished. Okay? But if you had multiple threads within that process, okay, each thread is now making blocking calls. Okay? So when that thread makes a blocking call, that thread blocks. Okay? But other threads in that process can continue execution, okay, which is why you get concurrency. That's the example I showed you. The first thread blocked, okay, when it called task and you called sleep, but the second thread could execute. The process as a whole is continuing to make progress, even though some threads are blocked. In a single-threaded process, one thread blocks, the whole process blocks. There's no progress until the thread unblocks. Is that clear? Okay. So you are essentially using the same blocking calls, but you get either concurrency or parallelism, and there is progress. Okay. There's a model between these two. Is called finite state machine or event-based models. Okay, though that essentially emulates the benefits of a multi-threaded process using a single thread. Okay? And to do this, you have to essentially make all operations non-blocking. Okay? This is also called asynchronous I/O. Okay? So if you make all operations non-blocking, you can get the benefits of multiple threads using a single thread. And I'll show you some code of how to do that, okay, just a little bit later. Okay? But right now we are talking about these two extremes, single-threaded process, multi-threaded process. So threads retain the idea of sequential process execution with blocking calls, yet they give us concurrency and parallelism. Okay? So from a software engineering perspective, you think of a larger application, you can think of components of that application. Okay? Each component can be executed by different thread. Okay? You don't need to have completely sequential execution. That can get you parallelism within that same process. Is that clear? Okay. So, so I'm going to now give you two examples of how you can make two applications that you might know about it, at least a web browser you definitely know, and a web server, and see how threads can help them become concurrent. Okay. Before I do that, I just want to show you another example, which is okay. So I don't know if you can see this, but this is the set of processes that are running on this machine, this activity monitor application. But if you look at any process and then you look at this column called threads, you will see how many threads are part of that process. Okay, you will see practically any application. So here is Docker, that's Slack, there's mail application, there must be there's Microsoft Word, okay, this Visual Studio, that's Google Chrome. You will see, if you go here, you will see that they are all multi-threaded. Okay? Practically any application that you run, okay, that's a modern application, essentially use threads underneath. Okay? Very few real-world applications are actually single-threaded anymore. They've all been made multi-threaded because every machine has many cores, so you can have that application take advantage of multiple cores on your machine. Okay? You'll see that the first one there is the kernel itself. that has 600 threads, 660 threads. Okay? So it's massively multi-threaded to do all kinds of things. But every other application, that's Docker, that's running at 90 threads. Right? So every application essentially works this way these days. Okay? So that's something you want to keep in mind. This is really something you should know how to build these applications, because that is how these applications are designed these days, to take advantage of the hardware that's on the machine. Okay? But now coming back to web browser. Okay? I just showed you Chrome just a second ago. That was multi-threaded. Every app, browser that you'll see is multi-threaded. What can we use these threads for? Okay, so if you think about it, the work that the browser does, okay, what are the things it would do? Okay, it will essentially go fetch web pages from a server or a network. Okay, you will then essentially get the web page. You can parse the page to see what are its components. Okay, you can do rendering of the page, which means you display the contents of the page on the browser window to the user. So there are different things a browser does, right? So you will make a connection to the server. You will download some content. You will process that content. You will display that content. At a minimum, it will do these things. It actually does a lot more than that. But you can think of each of these functionality being assigned to one or more threads. Okay? So if you want to essentially fetch some HTML page from a web server, you have one thread that's responsible for doing network communication. Okay? You want to then take some content that's been fetched from a server, want to process it, okay, parse it. You can have another thread that's responsible for parsing. Okay? Then you want to take the HTML page and images and render it on a window. You can have other threads to do that. Okay? So you can think of any application having some functionality. Each functionality can be assigned to a distinct thread, and that thread can then do that part. And then you get concurrency and parallelism for that application. Okay? So this is just a very simple example for you to understand how to take any application and think of its components and say, maybe that should be its own thread. It can be done by this thread, and this other component can be implemented using a different thread, and so on. That's how you can take an application and make it multi-threaded. Okay? So that's the client here, which is a web browser. Let's look at a server. Okay? So how is a server going to be multi-threaded? So first question is, you should ask, what inherent advantages do you get by making a server multi-threaded? Okay, the reason you want the server to be multi-threaded is it's waiting for requests from clients. That's what the server does. A server receives requests from clients, processes them, sends back responses. Okay? That's what a web server would do, but that's what any other server, like a database or a file server, would do as well. Okay? Now, a server will typically serve multiple clients, not just one. Okay? A web server can serve clients that are sending it requests from many different users all at once. Okay? So if you are going to receive multiple client requests more at the same time, okay, you can then say, why not use a thread to serve each request? Okay? So that will essentially allow you to get parallelism in your system. Okay? So fundamentally, you want to make a server multi-threaded so that it can serve multiple arriving requests concurrently or in parallel. Okay? And that's the picture that's shown here. Okay, that picture is a standard picture you should have in mind for any server application. Okay? Typically, what happens in a server application is there is a main thread is called the dispatcher thread, which is waiting for requests. Okay? And then there are a set of worker threads, okay, that are actually going to process the request. So the dispatcher thread receives the request, hands it off to a worker thread saying, go process this request. Okay? Because worker thread will actually do the work and send back a response. Okay? So in this example, you see there are 3 worker threads and there's one dispatcher thread. The dispatcher thread is listening on a socket, as I showed you last time. And as requests come in, it will just say here, it won't process it by itself. It will hand it to worker thread. The worker thread will execute that request. Okay? So if you have many requests coming, okay, they can all be serviced concurrently by assigning them to multiple threads. Okay? That's a basic architecture of any server application, multi-threaded server application. Is that clear? Okay. All right. So we'll go now into part 2, where we'll take this picture that I just showed you, okay, and we'll look at snippets of code that will make that work. Okay. So here, how does the dispatcher thread work? How do the worker threads work? And we'll look at that. Okay. So that brings us to concurrency models. And we are going to specifically look at concurrency for server-side application. We are not going to look at how do you make a web browser concurrent. but we look at how do you take any server, web server or any other server, make it concurrent. Okay. So here is essentially the main snippet of a skeleton of code that every server that you write will essentially use. Okay. Every server essentially has an infinite loop in it. Okay. It's called the event loop. Okay. And here's what the infinite loop does. Right. So it will wait for a request, it will process the request. Okay. And then it will wait for the next request process. So it will just, servers just sit in a loop waiting for requests and they process requests. Okay. So all servers you should think of, they're basically sitting in an infinite loop doing this. Okay. So now with that in mind, let's try to understand what is the code you are going to put in that while loop. Okay. Here's a sequential server, no threads. Okay. So essentially single process, single thread. Okay. You are processing requests, okay, sequentially. So your loop is going to be while you wait for a message. So you have while loop. So you wait for a message and you basically process the message. What are the message is a request in this case. Wait for a request, you process the request. Wait for the next request, you process the request, and so on. Okay. As the simplest server you can write. Okay. It has no threads in it. Yes, it's just a single while loop that just sitting and processing requests. So you should ask, what is the problem with this approach? Okay. So the advantage, of course, is very simple to write such an application. What are some disadvantages of this approach? Yes.
Processing the request.
Yes, so it's not using multi-thread, but that's not the disadvantage. The disadvantage, what you just said, is processing them one at a time. So if you get a request, you then start processing it, and another request comes in while you are processing it, just has to wait. You can't do anything. Okay. If 10 requests come in, they will all come and wait while the first request gets done, and then you will process the second request. All the other 8 are still waiting, and so on and so forth. So if there are concurrent arrivals, okay, those requests are going to be blocked for processing until you essentially get to each of those requests, because you're doing sequential processing. Okay. So a request will see long waiting times. Okay. The user that sent the request will just be waiting for a response to come while the request is just sitting there and the server queue waiting to be processed. Is that clear? So that's clearly going to be a disadvantage. So we now make this multi-threaded. Okay. The simplest multi-threaded server, this model. Okay. There are many types of multi-threaded servers we are going to see in the next few slides. The simplest one is called a thread per request model. Okay. So here's the snippet of code for a thread per request model. We're sitting in our while loop. Okay. So you wait for a request. Okay. So you wait until a request comes. Okay. Once a request arrives, you create a thread. Okay. That's the create thread. Okay. And you ask that thread to process that request. Okay. Every time a request comes, create a thread, you hand that request to that thread. Okay. Now, if multiple requests arrive, they don't have to wait for all the previous requests to finish, because each one will create a thread and hand it over, and then you'll take the next request and so on, and they'll all start executing on the server. Okay. So this is called thread per request because you created a new thread for every incoming request. All right. So advantage is newly arriving requests do not need to wait, unlike the sequential server that we saw. Thread is assigned to it for concurrent processing. The disadvantage is there is essentially frequent creation and deletion of threads. There's an overhead of creating a thread for every request arrives. Okay. There's going to be some overhead to creating a thread. It's not zero. Unlike a process which has higher overhead, there's going to be some price you pay here. Okay. So what do you think we can do to reduce this overhead? Yes. Pre-create all the threads and have them sit idle. That was actually the picture I had already showed you. Okay, so this is called the thread pool model. Okay. If you want to avoid the overhead of creating new threads over and over again, why not just pre-create a set of threads? They're all sitting there. There are worker threads. The dispatcher will simply take a request and hand it to an idle worker thread for processing. Okay. So that's essentially this code here. There's a thread pool model. Okay, so you first create the thread pool. It has size of n. Okay, so you created n worker threads, then you sit in a loop. You wait for a request. Okay, when a request comes, you no longer create a new thread. You look for an idle thread in the pool. An idle thread is one that's not already processing a request. Okay, and then once you get that thread, you ask that thread to process the request. Okay, So now you have avoided the overhead of repeatedly creating threads because you just created them when the server started, and then you're using the threads to process new requests when they arrive. Okay, all right. So one thread is the dispatcher. That was the same picture I showed you for the web server. So there's a dispatcher thread. The other threads are called worker threads. Okay, worker threads are the ones that will be either idle or they will be assigned a request to be processed. Okay, so the advantage here, avoid overhead of thread creation and deletion. You only do it once. Okay, disadvantage is how do you choose the right n? Okay, you have to decide how many worker threads to create. Okay, so how do you decide that? Is it 5? It is 10? Is 1,000? Okay, the answer is it's going to depend on the load on the server. The more concurrent requests it receives, the larger should be the thread size pool. Okay, the less busy the server is, you can make do with a smaller thread pool. Okay, but when you write your code as the developer, you don't know how busy the server is going to be at runtime. Okay, or when you start up this server, you don't know what to expect. Okay, so you will choose some n. Okay, at best, it's an educated guess. Okay, so if you underestimate, okay, more, so if you say n to 10 and 15 requests arrive, okay, the first 10 requests will find an idle thread and get processed. Okay, the remaining 5 will then be queued up waiting for one of the worker threads to free up, because you are not creating new threads here, unlike the previous model. The previous model, no matter how many requests arrive, you create new threads, so the threads never wait. Okay, in the sequential model, every thread waits because there's only one execution of a request at a time. Right? Here, if you exhaust the thread pool because all of them are busy, any additional requests are going to wait. Okay? So essentially, if more than n requests arrive concurrently, okay, then you are going to essentially have to make some requests wait. Those requests will see longer processing times. They will see queuing or waiting times. Other requests are not seen. So some requests will get good performance. Waiting requests will see slower response. Question is, does it depend on the number of cores? This has nothing to do with the number of cores, because we are just assuming concurrent requests. Cores are just going to speed up processing, but it's not going to do anything from a threads perspective. If you're 10 threads, whether you're 1 core or 10 core, if 11 requests come in, the 11th request still has to wait until the first 10 requests finish. In a single core execution, you will interleave the processing of these 10 requests. Okay? In a multi-core, you will actually get true parallelism. We'll look at that in just a few seconds. Okay, question is, can you create threads if a process is waiting and keep it around after it's done? Okay, so you can do that. So here, this is a simple model where the thread pool size is static. You picked n and you are going to use that n. You're not going to vary it. Okay? Of course, as I said, the load on the server keeps changing. So you can't never actually really know what is the right n. Either you pick it very large. You say its n is 10,000. So you have lots of threads. They'll always be sitting there idle doing nothing and waste system resources. Or if you pick it too small, you'll make them wait. Okay? So with static pool, you can only do one of these two things, but then you can make the thread pool dynamic. Okay? Now your server is getting more sophisticated, where you say you don't know the optimal size of the thread pool. Okay? You will start with some n. Okay? And you will vary n as the execution of that server proceeds. In particular, if the number of idle threads in the worker pool drops below a threshold, you will start new threads and add them to the pool. So you'll create new workers. Okay? Because you say, okay, the server seems to be getting busy. There are fewer and fewer idle threads. All the threads are busy. Let's increase the size of the thread pool by creating something. Okay? And vice versa. If the number of idle threads exceeds a high threshold, you will say, I seem to have too many threads. They're just sitting idle. Let's terminate some and reduce the size of the thread pool. Okay? So you are varying the size of the thread pool based on the load. As the load rises, the number of idle threads in the worker pool will drop. You will increase the thread pool size. As the load drops, okay, you will have more idle threads. You will start decreasing it. Okay? So now you no longer have to guess the right n. N will be decided at runtime based on the load the server sees. The server is itself adjusting the size of the thread pool based on the load. Okay? Any modern server will at least do this, okay? Because you don't know what the thread pool is or should be ahead of time. Is that clear? Okay, question is how much is the performance reduced if there's some number of idle threads? So what happens with idle threads is they increase the memory footprint of the process because every thread needs a stack. Okay, so it will allocate some memory for a stack. It has its own set of registers that typically saved when the thread is not executing. And then the server might sometimes execute idle threads, see that they're doing nothing, depends on the scheduler, and then waste some CPU cycle. That often doesn't happen if the thread is idle, but at least you will consume memory resources. Okay? The more the number of threads, the more RAM gets used. Okay? So you might see that the process is taking a large amount of the memory on your machine, even though it doesn't need to, because all the threads sitting there are idle. Okay? So it really wastes memory resources. Okay? Not CPU as much, because that can be done more efficiently. Yes. Okay, question, is there any hard upper limit on how many threads you can create? Okay, so there are two ways to answer the question. The real hard upper limit is the amount of memory you have in your system. Okay, if you exhaust memory, you cannot actually start. When you start another thread, the OS will say there isn't enough memory to allocate any more memory to this process. So that's the real hard upper limit, but typically you will not hit that limit because OS itself has softer limits on the number of threads, because you can have something that actually goes haywire and just starts creating threads. And then you don't want that process to cause the entire system to hang, right? Because that process can just start hogging all the resources on your machine. So the OS will often impose softer limits that you will hit before you hit the hard limit. Okay? But there is a limit. The real limit is if you run out of memory, you can't actually add any threads to the system. Is that clear? But that limit is typically very high. It's in the thousands or tens of thousands, because the threads are still very efficient. Okay. Any other questions here? Okay, so question is, when I talked about the client, I talked about each thread performing different functionality in the client. When I talked about a server, I talked about each thread serving a request. I did not talk about the server having different functionality and those getting executed by multiple threads. So remember that in a client, it's not that you have multiple requests. If you think about a web browser, if you click on a link, that's one request that the browser is processing. You are not going to click 10 things at once and expect the browser to do all 10 things. So you're essentially only doing one thing at a time. So it makes sense to take the application and split it based on functionality. Okay? In the server side, you are getting concurrent requests. So you want to split the work as per request rather than functionality within the server. So we divided the work two different ways. The client, we're dividing it by components of the application. In the server, we are partitioning the processing based on request arrival. You could have additionally said each request requires you to do 10 things on the server to process it. Should there be multiple threads, you could do that, but typically it's better to just have the thread do it all. Question is are the tasks sequential? They don't have to be. They don't have to, because what is happening typically is when you download a page from a browser, the page will start rendering while it's still downloading. So it's not like you wait for the whole page to download. So tasks can be concurrent. Okay. All right. So last model here is the asynchronous event loop model. Okay. So we looked at many different threaded model, but remember I said this model that tries to give us the benefits of multi-threaded processes with a single thread. Okay. The way you do this is you make your entire application, all of the calls that any function calls that a thread makes, you make them all non-blocking. Okay? And you use what is called an asynchronous event loop, where you essentially get events, and then you go to that event, you process the event, then you get the next event, you go process it, and so on. Okay? So in this case, you are using non-blocking calls, okay? Which is why it's called asynchronous. Asynchronous means non-blocking. Typically, synchronous means blocking. So you make all your calls non-blocking. your event loop is now serving events rather than requests. Okay, so and here are some examples of how essentially this works. So this is simple Python code. So you can actually look at what is actually happening here is you have a count function. It's essentially printing 1 and 2, but that sleep in that we had is now an asynchronous sleep, so it's non-blocking. So when you hit that, this function will cause that function will actually sleep, but you will not make the thread block. The thread that was executing that code will go back to the main event loop, start processing something else. Okay? So your code is now not executing sequentially for a single thread. You are jumping back and forth. Whenever you block, you jump to something else, process that, and you come back when this thing is done, and so on. Okay? So this is called asynchronous processing. Okay? That's the asynchronous version. We already looked at something like that earlier. Okay? For most of this course, you are not going to use any asynchronous programming. You're going to only use multi-threaded programming. But you should know that there is a way to build servers where you don't have multiple threads. You have a single thread. Okay? But that thread makes non-blocking calls, and it emulates the property of concurrency, because you're essentially doing more than one thing at once, because you don't block when you make a blocking call. You make that call non-blocking, and then you jump to some other part of the code and execute something. Okay? Yes, question.
Is it possible that we have
Okay, question is, in this case, when you sleep for 1 second, you sleep for more than 1 second, or will you get a call back? Whenever you have asynchronous calls, when that call finishes execution, you will always get a call back. Okay, so this asynchronous IO sleep will sleep for 1 second. When that sleep is done, the program, this main loop, will get a call back, and then you have to go back there and continue executing that process. Okay, so that's how it's going to work. So it is essentially callback. So as I said, it's event-based. The callbacks are the events that the main loop will process. The question is, if the thread is processing another task, will that callback wait? That actually depends on the asynchronous system. You can essentially immediately process it. It's like an interrupt, right? So you can immediately process it, or you can wait until you finish something. When you hit a blocking call here, you can say, what are the callbacks I've received, and jump and go process them. That will depend on the actual system. Yes. What do you mean by same? Okay. The question is it the same in threads, or is it differently? So what happens if this code was threaded, what would happen is a thread is executing this code. Okay. You call sleep. Okay. That sleep is blocking. So that thread is actually blocked. Okay. It waits. But the CPU scheduler will now jump to some other thread that's in the event loop and start executing that thread. Okay. So one thread blocks, you start executing another thread. You are emulating that same thing using asynchronous calls where there's only one thread, so there's no other thread to switch to. But when you come here and that you call this sleep, this is non-blocking sleep, so this function is going to sleep, but that thread goes back to the main loop and start executing something else, just as another thread would have taken over execution. So you have one thread that's doing the task of multiple threads, if you will, in this case. Okay. Is that answering your question? Yes. Yes. If the question is, do you go back once the sleep is over? In the threaded code, when the sleep is done, that thread will eventually start executing subsequent instruction. Same is true in the asynchronous. You get a callback, and you'll go back and continue execution. Right. So yes, that will happen.
This method better than using multiple?
Okay. Question: is this better than multiple threads? Actually, we'll get to that in just a couple slides, and we'll discuss what are the pros and cons of asynchronous versus concurrency and so on. Here is some more code. Here I already covered most of this. Just Python code that's showing you asynchronous event loops. Okay, they're basically doing what I just showed you, so I'm not going to go into too much detail here. There are two ways to write them. Okay, this is a simpler way where you can take any Python function and you make it use the async word, and that function actually starts making all of the blocking calls non-blocking. Right? So that just tells you, and then the main loop here, that's the asynchronous event loop that's just sitting and executing this asynchronous function. That's one way to do it. The other way to do it is actually when you make blocking calls, you have this thing called loop.stop that say that, okay, that's a blocking call, just go back to the main loop and start executing something else. And then there's a callback, go and start executing it. Right? So rather than making the function asynchronous, each blocking call, you decide whether you want to make it blocking or you want to make it non-blocking. You want to make it non-blocking, you are going to call this loop.stop that will essentially go back and execute something in the main loop. Okay? This is Python. In other programming languages like C, you actually have to change the function itself. You will never call print because print is blocking I/O. You will call an asynchronous version of print. So that by definition, the call that you are calling is never blocking to begin. Okay? In Python, you don't actually make the call, you have a different call. But in other languages, Java and C, you have for every type of blocking call, you have an asynchronous version of that call. That's what you will call. You have to make your system asynchronous. Okay. All right. So one more model, and then we'll do the comparison. The last model is multiple processes rather than multiple threads. Okay. Whatever I said about the server with respect to threads, you can think of building the server with more than one process. Okay. When the server starts up, it has a dispatcher process that is waiting for requests. Okay. When a new request comes in, it hands it over to another process that's part of the server application. So the server application is more than one process running. Okay. You can think of a dispatcher process and a set of worker processes. So dispatcher waits for requests, and when a request comes, you hand it to a worker process. The worker process processes it, sends back a response. Okay. So everything we have said about threads is now, this is called a multi-process server. Other than a multi-threaded server, it's a multi-process server. So everything we said previously is still true. Okay. You can have a static process pool. Okay. And then if you have more than n requests, those requests will block. You can make this process pool dynamic. Once you have fewer idle processes, you can start creating new processes and make the pool bigger and so on. Okay. So you can build your applications this way, or you can build them using threads. In both cases, you are going to get concurrency, and if you have multiple cores, you are going to get parallelism on top of concurrency. Okay. Now, this is a more heavyweight version to build a server than trying to do multiple threads for a server. Okay. The reason is when you are trying to now hand requests to other processes, you have to context switch to that process for that request to execute. Okay. And if you remember, earlier I said switching between threads is cheaper than switching between processes. Right? So if you use multiple processes to create your server, your context switch cost will be much higher because you are now switching to another request. You have to switch from one process to another and back and so on. But switching between threads or process, much cheaper. Okay. So then the question is, why would you use multiple processes to write your server rather than multiple threads? If it's more efficient to use threads, why even think of this model at all? Any thoughts here? Sorry? Crash. What do you mean by that? Okay. So yes, so I think that is indeed an advantage. If you have multiple processes, if one worker process that was scheduled processing a request crashes, the other processes, worker processes, can continue execution. They're independent processes. Just because one process crash doesn't impact the rest of the server. Okay? Not so in a multi-threaded process. If one thread crashes, the entire process is gone. Okay? Because if there's a memory corruption or something, it'll take down the whole process. The whole server will stop functioning. Okay? So this address space isolation, okay, basically each process has its own address space. So this address space isolation gives you benefits, robustness benefits, where if one or more worker thread crashes, the process as a whole will continue execution. Okay? But if you did it in the threaded case, that's not the case at all. Okay? Now, one example, there are many examples of process pool servers. So the Apache web server, which is the most popular web server that you see on the internet, it uses a process pool architecture. Later versions essentially then also supported threads, so you could configure it users either threading or processing. And the advantage was robustness. If you got a web request and it did some bad stuff and the thing crashes, the web server continues to work, okay, as opposed to multi-threaded server. Okay, some web browsers also use a process pool model. Okay? In particular, Chrome uses a pool model where every tab that you create in Chrome is its own process. Okay? So if that tab does something, it has some buggy code, and that something hangs, your browser as a whole will continue to work. That tab might disappear. The browser will not crash. Okay? But if you add all the threads as part of the same process, not a multi-process model, if one thread crashed because of some buggy web JavaScript or some code that you downloaded, your whole browser will hang or crash. Okay? So it gives robustness, which is why some applications use this model. Even though it costs, there's a cost associated with it. Is that clear? Yeah. Yeah. So question is, if I understand your question, it's saying, how should you design the server? Should it be multiple processes, multiple threads, asynchronous perhaps? Okay, the answer is going to always depend on what are the design goals. Okay? There's no one answer. Okay? If robustness is really important, okay, you might want to be willing to pay the extra price by having multiple processes that are part of that application. If efficiency is important, maybe you make a different design choice. Right? So you have to really decide as a design application developer or a designer, what is the right model that works for your application. Okay? There's no one answer that's the right answer. Okay? But at least there is an answer if you just want to think about efficiency. Okay? Robustness, let's put aside for now. Okay? We can compare these models on the efficiency axis. Which one is the most efficient? Okay? So here you have the sequential, we looked at that, concurrent, which is basically multiple threads. Okay? We also looked at pure sequential, thread-based, we looked at event-based, and process-based. As we've seen 4. Okay? We saw many variants of the thread-based, but for now, just assume any variant you want, doesn't matter. Okay, we'll ask which one is the most efficient. We're not now worried about which one is robust to crashes and so on, which one can give us the best performance. That's the question we want to ask. Okay? So we can order them. So this one is going to be the least efficient. Right? Sequential, we already said, has the longest waiting time. This is not going to win. Okay? So we'll just put that aside. So then the question is between event-based, thread-based, process-based, which one is more efficient? Okay? We can at least compare these two, the thread-based and process-based. Okay? And we can ask which of these two is more efficient. Okay? It should be thread-based because I already said context switching for processes is more expensive. So for the same set of requests, the process-based architecture will consume more time, not consume more time, it will take more time to process that request because the context switching will add to the overall overheads. Okay? So thread-based, more efficient than process-based. Both thread-based and process-based, more efficient than sequential because both of them are concurrent. Okay? Then the question is, where does the event-based sit as compared to those two? Any guesses or comments? Sorry, it's after process, least efficient? Is that what you just said, or most efficient? Everything is better than pure SQL. That is a given. This is the won't be least efficient. Okay. Okay. So in between thread and process. Okay, there are only 3 answers. It's worse than those two. It's here or it's here. There are no more than 3. You can only place it in one of those things. Okay. So the answer is actually it depends. There's no it will depend on what is the hardware configuration of your system. If you have a single core machine, okay, only one processor, okay, event-based is the most efficient of the lot. Okay, because there's no context switching at all. You removed context switching. Right? This is switching between processes. This is switching between threads of the same process. This has a single thread. It's just jumping around in function. We eliminated all context switches because everything is asynchronous. So by definition, you will actually get better performance than those other two. Okay? So if you want to build a really high performance server, okay, you will actually spend that time to write that event-based. It's harder to write because the code is more complicated, but it will give you your efficiency benefit. Okay? For a single core system, event-based architecture is no context switching. So you are going to, by definition, get better performance. Okay? So what happens if you have multi-core system? Yes.
The event-based can not take it multiple.
So if you have a multi-core system, event-based as a single thread, right? So it can only by definition use one of the cores on your system and no more, right? Thread-based, if you have 2 threads, they'll run on 2 cores. You'll get twice the throughput. Process-based, if you have 2 processes or more worker process, they'll run on those cores. You'll get more throughput. Okay? So on your multi-core, the event-based will actually no longer be the most efficient. It will be the least efficient because you are not able to take care of parallelism. You cannot take advantage of multiple cores. Okay? So that's why I said the answer is it depends. Of course, if you want to retain the benefits of the event-based architecture in a multi-core system, you have to have a hybrid model where you basically make a multi-threaded event-based system where you have more than one event loop. Each one of them is running on a core. You have 4 cores, you will create 4 event loops. Each one of them is doing asynchronous process. Okay, then you'll get back that advantage. But that's not a model we talked about. But that's really something system designer would do if they want to run their servers efficiently and take advantage of the hardware resource. Okay? But the simple answer is if you're a single core system, these are the most efficient, the event-based the most efficient way to write servers. In a multi-processor or a multi-core system, okay, you will not get the advantage of hardware, so you will essentially be getting less throughput than multi-threaded or multi-processor. Okay, yes, question. Okay, yes, the question is even within a multi-process system, can you have multiple threads? You can actually have the hybrid between thread and process-based. The Apache web server actually does that too. You can have multi-process and multiple threads. But typically, if you have an event loop, you have to really think about what do those threads within a process do. So if you have a request that you handed off to a process in a multi-process model, and that server itself has multiple components that you want additional threads to do processing, then you can add threads to the process. So the request is handled by multiple threads, not one thread within that process. So it gets you some additional benefits. It also makes the server more complicated. So these are just baseline models. You can combine some of these, as you can see, to get hybrid versions of those models as well. Is this clear? Okay. All right. So that just brings me to the last point. I use these terms concurrency and parallelism. Okay. We should define it carefully so you understand what they mean and how they are different. They're not the same thing. They kind of sound similar, but that's not really the case. Okay. So concurrency basically means it enables the handling of multiple requests. You're not doing sequential processing. You can handle multiple requests using threads. Okay. Request processing does not block other requests. Just because you're processing one request doesn't mean other requests that have arrived are blocked until this request is finished. This is what we got with threads. Okay. You could essentially interleave the processing of multiple requests. Okay. But concurrency does not by itself give you true parallelism because you can get this interleaving even on a single core. Okay. Now, when you have multiple threads and you have multiple cores, you are going to get true parallelism. That means more than one thread is actually running at the same time. Okay. This does not, concurrency by itself doesn't mean 2 threads are running exactly at the same time. It just means I can interleave the processing of multiple threads. Okay. And you can have all requests make progress. Okay. But one request at a time, a little bits of a request at a time, not one request at a time, but you can interleave. Okay. True parallelism gives you actual benefits of running on multiple cores. And I'll go show you an actual example to make that more clear. But is that more, at least the definition is clear. So parallelism gives you more than concurrency. Parallelism requires more than one processor. Concurrency does not require more than one processor or core. You can get concurrency with threads on even on a single core machine. And you can serve multiple requests and so on. And I'll give you an example that will make that clear in just a few seconds. Any questions before we switch to thread scheduling and try to get a little deeper into how threads work? Okay, so we'll now talk about thread scheduling. Essentially, if you have a process with multiple threads, how are they scheduled by the underlying OS? What concurrency benefits do we get, and so on. Okay? So to understand thread scheduling, we should understand a little bit about how threads are implemented. Okay? So by and large, there are 2 types of threaded implementation. There's something called user level threads, and something called kernel level threads. Okay? User level threads are essentially thread packages that are implemented as libraries as part of some application. Okay? They do not require any OS support. They do not directly use any OS support. And neither are those threads visible to the OS. Okay? They're visible to the application. Application can create threads, delete threads, and so on. They're all implemented in a library that's part of the application. Okay? The OS has nothing to do with them. Okay? It's the application managing the threads, creating threads, and so on. Okay? Kernel level threads, on the other hand, as the name suggests, basically is the OS providing support for threads. Okay? So essentially, all applications can now take advantage of it because the OS provides support, and the OS is involved in the creation of threads, managing threads, scheduling threads, and so on. Okay? So that's the way you want to understand it. So any thread package can be either of one of two flavors, user level or kernel level. Okay? So what are some pros and cons? Okay? So here are some things to keep in mind. Okay, let's start with user level thread. Here, the advantage is you don't need to make any changes to the OS to support multi-threaded application. Even if your OS has no support for threaded application, you can still write multi-threaded application because it's part of the library that's part of the application. So for example, you might have a Python library that implements threads without using any OS stuff. You can still now write multi-threaded code. Okay? All the threads in this case will be managed by the runtime, okay? Not by the OS. Okay? It's very efficient because creating, deleting threads are library calls because the entire threads package is implemented as a library. So there are function calls for library inside the process. Okay? Really lightweight, very efficient. Okay? It's very flexible from a scheduling perspective because the threads are now scheduled inside the library. Okay? So if you have two applications that use two different threading packages, user level threading packages, each can pick its own scheduling algorithm that's best for that application. Okay? You are no longer bound by what the OS is doing. Okay? OS's scheduling algorithm is independent of the thread scheduling algorithm that the application uses. So you can pick a different one, okay, in that threads package to get flexibility. Okay? Disadvantage of user level thread package, okay, is the fact that the OS doesn't know of the presence of threads. The OS sees this entire process as a single threaded process. It does not know that there is a library inside that process that has created user level threads. Okay? So if one thread in that process makes a blocking call, okay, the OS will assume the process made a blocking call and block that entire process, even though there are other threads in that process that are ready to run. Okay? So the main disadvantage of user level threads is because the OS does not know of the presence of threads. If any thread makes a blocking call, then the process is going to block. Okay? You cannot make progress for other threads. Okay? Threads will compete for one another inside the process. Okay? And furthermore, you cannot take advantage of multiple cores because the process looks like a single threaded process to the OS. So it's not going to schedule that same process twice on two cores because it thinks it has only one thread in it. Right? So you cannot take advantage of multiple cores, even though you get concurrency benefits, you can't get parallelism benefits. Okay? So here's a picture of user level threads. So you have a process, three processes. Each process, these things here are threads, these arrows. Okay, you will see that there's a library scheduler, okay, and then there's OS scheduler and processors or cores. Okay? So what you will see is essentially each of these processes is seen by the OS scheduler as a single threaded process. Okay? So the OS scheduler will pick one process for execution and assign it a processor or a core. Okay? And the library scheduler will then decide, because this process is executing, which of its threads should execute. So it will make another scheduling decision. And it will pick one of these threads for execution, and that's the actual thing that will run on that process. Okay? So two-level scheduling decision. The OS picks a process, and the library scheduler inside the process picks a thread for execution, and then you're done. Is that clear? Okay. And you will see that the OS doesn't know there are three threads. So it will only pick this process once, and it will only run on one core. It will never have two threads from the process running on that two processors at the same time. The question is, how do you get performance benefits? You're still getting concurrency benefits, right? So you're not getting true parallelism, but concurrency benefits are still there because you have multiple threads in a process. Okay. So here are kernel level threads, right? So everything is now flipped. So whatever I said for user level threads in terms of OS benefits and disadvantages are all opposite. Here the kernel is providing native support for threads within application. The kernel creates and deletes threads for each process and hence knows how many threads are present in a process. It can explicitly schedule a specific thread directly for execution. Okay? And that is shown here. So you will see now that the same situation as previous, 3 processes, 3 threads. Okay? You will see that all of these threads are now visible inside the kernel. Okay? So now OS scheduler is no longer picking a process for scheduling. It's picking a specific thread within a process directly for scheduling. Okay? So in this case, you will see that the OS decided that it's going to pick 2 of these threads for execution. So now you have essentially true parallelism where 2 threads of the same process are executing on 2 different cores or processors. Okay? And all of these other threads are blocked, which is why they're grayed out. But you could have picked thread 1 from process 1 and thread 3 from process 3. Okay? That's what the OS scheduler will pick. In the previous case, you only pick the process, and then the library scheduler picked the thread. Here, you can directly choose the thread for execution. You can get advantage of parallelism and so on. Okay? But it will have more overhead because kernel has to be involved in creation and deletion of threads. So thread creation is a system call in kernel level thread. It's a library function call in user level thread. Much cheaper in the user level threads than it's in kernel level threads, but you get some advantages. Right? The disadvantage, of course, another one is you are bound by whatever the OS scheduler policy is. You can't pick your own policy like you could do in the user level thread packages. Is that clear? Okay. All right. So now we'll do a quick example. So you will understand concurrency and parallelism at least. Okay, so here is our program. Okay. This program has 2 functions, foo and bar. Okay. Initially, we'll assume that this program is just a single thread. Okay. It's just executing. So from a logical perspective, okay, x-axis is time, the foo function will execute first and then the bar will execute next because they are invoked one after the other. Okay. Now, because we have used the OS scheduler doesn't actually execute that way. The way OS schedulers work is they use something called time slicing, where each process is scheduled for a time quantum. Okay. When the quantum expires, the OS scheduler can pick some other process for execution. Okay. So processes get to not run forever, they get to run for a small time slice. Usually it's 10 milliseconds or 1 millisecond or something like that. Okay. Now for simplicity, we'll assume this is the only process in the system. So when a time slice expires, the OS scheduler has to pick that same process because nothing else to run. Okay. So essentially that's what you are going to see, where you have essentially the 6 time quantums. The first one ran the first part of foo, the time quantum expired, you pick the same process again, it ran some more part of that code and so on. Okay, so essentially you'll run the green function in 3 quantums and then sequentially run the red function in another 3 quantums. Okay, still sequential execution, same as this, but it's now showing the presence of quantums, and that's how actually the OS is scheduling them internally. That clear? Okay. So now let's say that you have multiple threads, right? So you assign 1 thread to foo and 1 thread to bar, okay? And they're kernel level threads. So the OS knows that they are present, and you are doing time slicing. Okay? So the first thread is going to be chosen. Let's say you pick the green thread, it will run for a time slice. When the time slice expires, okay, the OS will now pick some other thread. In this case, there's a red thread, so it will run for a time slice. Okay? And you will come back because you can do round robin scheduling. So you will come back, you will do green, and then you'll do red, green, and so on. Okay? That is actually what concurrency means. Both threads are making progress. Okay? You're making progress 1 quantum at a time, 1 time slice at a time. Right? So it did no longer executed that whole function and then switch, because you're multi-threading. There's 1 thread doing the green part of the code and 1 thread doing the red part, and you're switching back and forth. So both threads make progress. Is that clear? Okay. So we'll now add one more detail here. We'll assume that the threads now also do I/O. Okay, we didn't have any I/O, so you could just continue execution. Okay. So let's start with the sequential case, no threading. So we'll assume that this has two print statements and bar has two print statements. Each time you do a print statement, that's IO because you're writing to a screen, so you will block. Okay. So in sequential execution, okay, you will run the green function for a quantum. Let's say you call the print statement, and the entire process blocks. You're doing IO, nothing can run. The CPU is idle at this point. Okay, there's no other process to run in the system. If there's some other process, that's what would execute, but here you have nothing. So the CPU is white means the CPU is idle. So you are doing IO. Once IO is done, you execute the next quantum. You again run the green function, single one thread. Right? Then you do IO, then you do green, and then you do the same thing for red. Okay? So then the question is, now if you go back to multiple threads, okay, what will this picture look like? Yes, let me show you what it will look like. So that's what it's going to look like. Right? So you run the green function for one quantum. We'll assume exactly at the end of the quantum, it's the IO. Okay? The green thread is blocked. So the IO is blocking. Okay? So you can no longer run the green thread. Now the CPU scheduler, is there another thread to run in the system? There is one, that's the red thread. So it will schedule that for execution. Okay? That will run for a quantum, and then it will do IO, and that thread will block. Okay? Now if the green thread is not done with its IO at that point, nothing can run because there's nothing available to run. But we'll assume that the IO finished in that quantum in this example. So you can, the green thread has become runnable again. So you run the green thread, and it does IO again. Right? And then again, if the red thread was not done with this previous IO, you will have idle CPU, but assume it was done, you can switch to the red and so on. So you will now see that the CPU, the single core, is continuously busy, and when some threads are doing IO, others are running on the CPU and vice versa. Okay? So the CPU, so you are now getting same interleaving with IO. Is that clear? Okay. So we have one more thing, and then we'll stop here, which is now we'll add a core. So we'll have two cores, not one. Okay. So what happens in this case? Okay, you have two processors in the system. Okay, there are two threads. So CPU scheduler will take the green thread, put it on one core. You take the red thread, put it on the second core. Okay, each of them will run for a quantum. They'll both do IO. They'll both block. Okay, now, there are no other threads, no other application in our toy example. So both of them will do IO, and both cores will be idle in this case while the IO completes. And once the IO completes, then both threads will run again. They'll both be idle and so on. Okay. Of course, there are other applications in the system. When these two threads are doing IO, you will run something else on those cores. But in this example, only one application with two threads. So this is true parallelism because you have two threads running at the same time. These are all concurrent executions, only one core, but each thread is making progress without waiting for the full function to finish. Okay, so that should give you a clear picture of how concurrency is different from parallelism. Is this clear? Yes, last question before we end. A single core can execute one instruction at a time, or one thread at a time to be more precise, and the thread is executing the instruction of that core. Yes, one core means you only run one instruction. Processor executes one instruction at a time. Okay. Anything else? Okay, so we'll stop here. We'll continue.